Welcome everyone. We'll continue our talk about the least square estimates, and we are going to talk about the properties of the least square estimators. First, we are going to talk about random signals and their properties, and we'll follow that by a description of the statistical properties of the least square estimates. Then we'll talk about the geometrical interpretation of the least squares, and finally we are going to introduce the RMAX model, which is a stochastic model commonly used in parameter estimation. So if we assume that we have a signal and that signal is changing randomly, something like this, all over the place, if we would like to calculate the mean of that signal, and it's also called the expected value of that signal, we can actually assume that this value is just the equivalence of the average. However, this requires as an assumption that each point on the sequence will have the same probability of occurrence. So if this is true, we can take this value, say, as the average value or the mean value. Okay. Now, we can also calculate the variance, which is defined as the expected value of the signal minus its mean, all squared. And actually, the physical meaning of the variance is that it gives an indication about the fluctuation of the signal around its mean. So we normally take a band. Within that band, most of the values, not necessarily all the values, but most of the values are within this band, and the width of that band for normal distribution is normally 3 times sigma, where sigma squared is the variance. Of course, this is known as the standard deviation of the signal. So as a conclusion, the variance gives an indication of how much the fluctuation of the signal around its mean. If we take a vector of signals x, and each of these signals is a function of time, we can find the mean of that signal, and in that case it would be the mean for every signal. So this would be the mean of x1, mean of x2, and so on up till the mean of the signal xn. So this is the mean of vector of signals. The covariance of that signal would be composed of a matrix, and that matrix will have at the diagonal elements the variance of, say, x1, the variance of x2, and so on up till the variance of xn, and of the diagonal elements would be the covariance of x1 and x2, and so on. So this matrix is normally a symmetric matrix, and the of diagonal elements is called the cross covariance. This is defined as the expected value of x minus the mean times x minus the mean transpose. This is the definition of the covariance matrix. And actually the off diagonal element, like here this element, this gives the relation between x1 and x2. So if they are independent of each other, the value here will be 0. However, if they are related or correlated to each other, then if the value is positive, that will indicate that an increase in x1 would lead to an increase in x2, and if it is negative, then the opposite will happen. If we have two signals x and y, and we assume these two signals to be independent. So the expected value of their product would be the expected value of x times the expected value of y. And in that case, if one of these two signals has zero mean, then the expected value of their product would be just zero, and that will happen in our analysis of the least square estimator, as we will see later on. We also need to introduce the concept of white noise, and actually the word white is coming from light. In white light you'll have all the colors in the spectrum, and in white noise, in the power spectrum of the signal, you will find all frequencies represented. So anyway, the white noise is an independent sequence, so it will have an expected value equal to 0, and the variance is constant, equal to sigma squared, and there is no correlation between any point and the other point around it, and the power spectrum is constant and equal sigma squared over 2 pi for all frequencies. So this summarizes what we need regarding random signals. Now we will go back and see the statistical properties of the least square estimator. Now we recall the equation that relates the measurement y to the true parameters of the system, and possibly some measurement noise or errors that are included in the modeling equation. Now I is the sampling index that varies from 1 up to t, where t is the number of samples, E of I is an independent sequence of zero mean, and phi is a vector of known functions, and psi is a vector of true parameters of the system, which is normally not known, and yi is the measured output. So we have shown before that the least square estimate of the parameter theta would be given by this formula. So this theta hat is just the estimate of psi. The vector y would be composed of the measurements y of 1, y of 2, up to y of t. The number of measurements is t. And phi will be composed of row vectors phi 1, phi 2, up till phi t. This is the phi matrix. Now there are three main properties of the least square estimator. I'm going to prove the first and second. The third, actually, I will leave it and maybe I will put a PDF file that explains its proof because it's a bit long. So now let's define the different symbols here. V, as we have seen before, is 1/2 the summation of the errors squared. So if we call the error epsilon square from 1 to t, and this is E transpose times E, the vector E, which is composed of the errors in each measurement. T is the number of samples, and N is the number of parameters to be estimated. So here, for example, the expected value of the estimated parameter would be just equal the true value. The covariance of the estimated parameter will be equal to sigma squared, where sigma is the standard deviation of the error or the noise signal, and phi transpose phi is as defined before, the matrix phi that is composed of the known functions. V, we have defined V here, and T is the number of parameters to be estimated, and N is the number of parameters. So if we don't know the variance of the errors or the noise in the signal, we can calculate an estimate for that. Okay, let's consider the equation for the measurements y as phi times psi plus E, where E is a vector of the calculations or measurement errors. I'm going to multiply this equation from the left by phi transpose phi inverse times phi transpose y. So in the right hand side of the equation, I will have here phi transpose phi inverse times phi transpose phi psi plus phi transpose phi inverse phi transpose E. Now we know that this left hand side of the equation would be just the estimate theta hat, and these two matrices are just the inverse of each other, so their product will give the identity. So this equation can be written as theta hat equals psi plus phi transpose phi inverse times phi transpose E. If I take the expected value of the equation, of course, the expected value of psi, which is the true values of the parameter, will just be psi itself, and the expected value of the second term here would be just the expected value of E, since the matrix phi is composed of known functions and values. So that would be phi transpose phi inverse times phi transpose the expected value of E. But since E is composed of a sequence of 0 mean, then the expected value will be 0, and that will give me the required result psi. So that means actually is that if we do the experiment in ideal conditions, we guarantee that eventually the average value of the estimate will be equal to the true parameters, which means that it will converge to the average value will converge to the true parameters of the real system. Now, the second property that we would like to prove is the covariance of the estimate. How much is the fluctuation of the estimate around its mean value? If we like to do this, let's calculate first theta hat minus the psi, and that would be equal to phi transpose phi times phi transpose E. This comes from this equation actually, just direct substitution from here. So the covariance of theta hat would be just the expected value of theta hat minus psi times theta hat minus psi transpose. This is the definition of the covariance. So I'm going now to substitute for theta hat minus psi from this equation here. So that would give me the expected value of phi transpose phi inverse here times phi transpose E, and then the transpose of this quantity. So I will just rewrite the equation, but I will reverse the order of the vectors and the matrices and take the transpose of them. So that would be E transpose times phi transpose phi the transpose of the inverse. And again, since phi is composed of known quantities, then I will just have to take the expected value of E times E transpose, and that would give me actually sigma squared, and we'll get phi transpose phi inverse times phi transpose phi times phi transpose phi inverse. Now, since this is a symmetric matrix, so its inverse is also symmetric, and the transpose will be just the matrix itself. So I can eliminate the transpose from here, and if you take the product, this will give you the identity matrix, and the final result would be sigma squared times phi transpose phi whole inverse. So this is the expression for the covariance of the estimate. Actually, this is in the literature. This matrix phi transpose phi inverse is actually called the covariance matrix, as we are going to do in coming lecture. Okay, I'm going to represent the vector of measurements like this, vector y. And the vector which represents the computed value of y, which we called it before y hat, I'll represent it like this. And y hat is not necessarily in the same plane as y. Now, we know the relation that we have used to relate y and y hat. We say that y is equal to y hat plus an error vector, where y hat is equal to phi times theta. So in that case, what we would like to do, if this is the vector E, we would like to select the estimates theta so that the vector E would be as small as possible. And we know that the smallest distance from this point, the tip point of y and the tip point of y hat, would be a vector perpendicular on the vector y hat, or the plane that includes the vector y hat. We also, I'm going to assume here for simplicity that I have just two parameters to estimate. I can also write an expression for y hat as phi 1 times theta 1 plus phi 2 times theta 2, where phi 1 and phi 2 are just the columns of the matrix phi. We can write this expression, and in that case I can represent this summation in terms of two basis functions. The first one, I'm going to call it phi 1, and the second one, I'm going to call it phi 2. And what we normally do is to select theta 1 and theta 2. So I will project the vector y hat on the basis functions. So what I get here is a length equal to theta 1 times phi 1, and I get here a length theta 2 times phi 2. So what we did here is that we tried to form the vector y hat such that the projection of y, the perpendicular projection of y, would give me the tip point of y hat. If that happens, then I will guarantee that I will get the least square or the minimum possible error E. Now, in order to do this, or to represent that mathematically, it means that the vector E is perpendicular on the plane that includes phi 1, phi 2, and y hat. So it has to be perpendicular on each vector in that plane. So I would write then that phi 1 transpose, the inner product of phi 1 and E is equal to 0, and the inner product of phi 2 and E is also equal to 0. I can combine the two equations together, so I will get here phi 1 transpose and phi 2 transpose, and that will give me the matrix phi transpose. So I can write then that phi transpose times E is equal to 0, but E, as we defined it, is just the difference between the measurement vector and the computed vector y hat. So that's y minus phi times theta. So that means I should have phi transpose times y minus phi theta equal to 0, and that will lead to phi transpose y equals phi transpose phi theta. So the least square estimate theta would be just phi transpose phi inverse times phi transpose y. This is of course the same answer that we have shown before. So this is the geometrical interpretation of the least squares. It tries to find the values of theta 1 and theta 2, the estimated values, such that the error vector would be perpendicular on the plane that would include the basis function, which are the columns of the matrix phi, and include the computed value of y. Okay. Let's define T as the sampling index. So the forward shift operator, which is Q, is defined as if you multiply Q by y of t, you get y of t plus 1, which means that you advance the signal one sample ahead. Q minus 1 is also defined as this. If you multiply Q minus 1 by y of t, then the signal is shifted backward one sample. The Rmax model is then defined as a polynomial A multiplying y and a polynomial B multiplying u, polynomial C multiplying E. So as an example, if we consider a system in the frequency domain represented by transfer functions like this, we can switch this system to the time domain. I will just substitute for that by Q. So I get Q plus B over Q squared plus A1 Q plus A2 times U plus Q plus C over Q squared plus A1 Q plus A2 times E of t. Now what is the difference between Q and Z? Actually, this is just a type of notation. However, the essential difference is that Z would allow you to take initial conditions into consideration, while Q is considered to be something in the time domain to get the difference equation given the transfer function of the system. This is very similar to the Laplace operator S and the operator d by dt, which we have given the notation p before. This is the same analogy actually in discrete time. Anyway, if you have this relation, then you can actually write this as q squared plus a1q plus a2 times y of t equals q plus b u plus q plus c multiplying e. So this is the polynomial A, this is the polynomial B, and this is the polynomial C. And if we like to get the difference equation for the given system, we can write then y t plus 2 plus a1 yt plus 1 plus a2 y of t equals ut plus 1 plus b u of t plus e of t plus 1 plus c e of t. Now, what is the effect of having this polynomial acting on the white noise? This is white noise. Actually, the result of having this signal filtered like this is that you produce color noise, and that is actually a violation of the conditions that we have used in the least square estimation in order to conclude that the expected value or the average value of the estimated parameter is equal to the true value. If the signal E is no longer white noise, color noise like this, then we cannot conclude this property, and then there will be some bias in the estimates of the parameters if we are using the pure least square estimates as we have done before. So this is a topic that we are going to discuss later on, but this is just a hint on the topic right now, and later on we'll see how to compensate for the effect of color noise. Okay, thank you.